Hello everybody, this is Arif. Today we will solve an integral which is given as from 0 to infinity 1 over 1 plus x cubed dx. Okay, so it looks like an innocent one, but in the end it is a little bit tricky. Okay, so the deal for today is we will use the residue theorem. So we will use complex calculus to evaluate this integral. There are actually other ways to do it, but for the purpose of practicing the residue theorem, we will just go with that route. Okay, so if you are ready, we will start now. First of all, we will define a function which will have a complex argument, variable z, right? So which is going to be like this integrand here, so 1 over 1 plus z cubed, right? So since we'll be working on the complex plane, right, imaginary and real axes, we need to find the poles of this function. This is our first thing to do. So 1 plus z cubed is equal to 0. So the roots of this denominator will give us the poles of this function, okay? So z cubed is equal to minus 1. So what is minus 1 in terms of the polar coordinates? So it's going to be e to the I pi. I hope you all remember that. And we actually have the support here, e to the I pi plus 1 is equal to 0. So e to the I pi is equal to minus 1. This is good. So now, on the complex plane, as you may remember, so let's draw it. So we have a real axis and we have an imaginary axis, okay? So e to the I pi is somewhere here, right? So it's minus 1, e to the I pi, okay? So if we make one rotation here, so one full revolution, okay, I end up at the same point. So if I move 2 pi radians here, so I end up with the same point. So here, I can simply put k times 2 pi, where k is an integer, right? So k could be 0, could be 1, 2, 3, 4, 5, okay? So when we use this, and when we take the cube root of both sides, we will actually have 3 roots. So this is how we get 3 roots here. Because this is a cubic, so the cubic should have 3 roots, right? Complex roots, of course, complex. So here, k is equal to 0 corresponds to the first root, k is equal to 1 corresponds to the second one, and k is equal to 2 will correspond to the third root. Okay, keeping that in mind, z1 becomes, so when k is equal to 0, we have e to the I pi. When you take the cube root, you get e to the I pi over 3. Okay, so pi over 3 corresponds to like 60 degrees, right? And it has magnitude 1. So the modulus 1, okay, and 60 degrees. So we are somewhere here, right? So this is my z1, which is equal to e to the I pi over 3. Okay, so what is z2? So z2 is going to be equal to e to the I. So when k is equal to 1 here, we have 3 pi. Okay, 3 pi over 3 is just pi. So this is actually my second root, z2. Okay. So what is the third root? E to the I. So when k is equal to 2, we have 5 pi over 3. Okay. So the other root will be somewhere here. Okay. So z3 is equal to e to the I 5 pi over 3. So 5 pi over 3 is nothing but 300 degrees, right? So it corresponds to a 300 degree rotation. 5 pi over 3, okay? So these 2 points are actually symmetric across the real axis, right? So they will have the same real value, okay? So the real value of z1 and z3 are the same, okay? So we found the roots. So these are the poles of this function f of z, okay? And then we will move on from here. So far we have defined this function f of z on the complex plane, 1 over 1 plus z cubed, and we found its poles, okay? And it turned out that z1 and z3 were symmetric, so they have the same real values, okay? And their imaginary values are different from each other with a sign, minus sign, okay? So the next step is to choose a contour. So we will define a contour integral. Okay. So for the contour, so this is my origin, I will choose, so this is R. So on the real axis, I will move along the real axis from 0 to R. So this is part of my contour. So when I reach R, I will start to move on a circular arc. So this is my circle, which is, let's say, C2, this is C1, C1 line, C2 line, and then I'll move back to the origin in the radial direction. So this angle here is going to be called theta star. So I don't know what theta star is, but I will determine what it is while solving the problem. So z1 is equal to e to the I pi over 3 here. Okay. So as you see, my contour includes only this pole. So there's only one pole inside the contour I chose. So if I define the contour integral f of z dz integral, the closed contour, okay, by residue theorem, what it says is this is equal to 2 pi I, the residue of f of z at z is equal to z1. So since there is only one pole, I just need to calculate the residue of that function at that pole. Z is equal to z1. Okay, and this will give me the integral of on this contour, okay, of f of z. So this integral is not equal to that integral. You already know that, but somehow using this, we will try to find the result of this. Okay. Before we move on, I would like to remind you that this is the integrand here is a real function, right? 1 over 1 plus x cubed, and the limits here are real. Okay. So in the end, the result of this integral has to be real, right? So don't be scared with these I, okay, I term, and also all these complex numbers. So in the end, the result of this integral will turn out to be real, okay? So you just need to make sure that. Okay, so if we are all clear, we will move on from here. We will first find the left-hand side of this contour integral, okay? So if I look at the left-hand side, so I first move on C1. So I'm on the real axis, so Z is nothing but X, right? Z is equal to X. Okay, so on C1, if I move on C1, I simply move from 0 to R. Okay, this is good. So this becomes dx over 1 plus x cubed. That's it. Okay, so 1 over 1 plus z cubed becomes 1 over 1 plus x cubed. So this actually looks like my goal integral, right? So as long as I take this r go to infinity. So at some point I'll take this r, okay, go to infinity. So this is going to be exactly same as this integral. Okay, plus, so I'm now moving on C2, right? We need to be careful here. So if I move on C2, the z values change as r times e to the I theta, right? So r is constant for all points on C2. The modulus is the same, r, right? So the angle is different, e to the I theta. So theta is my variable here, okay? So this is the polar representation. I hope you all know that. So dz is simply equal to r times, because r is constant, I take the derivative with respect to theta. So this gives me I e to the I theta d theta, right? Okay, so here what I can write is for C2, okay, so this is d theta, so I can write r I e to the I theta d theta divided by 1 plus z cube, which is r cube e to the I 3 theta. Okay, so here theta changes from 0 to theta star. So far I haven't defined what theta star is, but we will do it in the next step. Okay, after C2, now we are moving on the C3 line. So let's see what happens on C3. So if we are moving on C3, what happens is z, my z value, z variable, changes as r times e to the I theta star. So all the theta values are equal to theta star, right, in terms of this polar coordinate. But my r is now a new variable. The modulus changes, right? The distance from the origin changes. So dz is simply equal to e to the I theta star dr. Okay? So now the third integral on C3 will be equal to e to the I theta star, okay, dr over 1 plus r cube e to the I 3 theta star. Good. So these are the three integrals which in the end give me this contour integral, okay? At this point, so we are ready to take this limit, r goes to infinity, right? So when we take limit, r goes to infinity, okay? When we take the limit, r goes to infinity. Well, by the way, here, this little r changes from r to 0, right? So we move from here to here. Okay, this is good. Okay, so when we take this limit, what happens is the upper limit here becomes infinity. This lower limit here becomes infinity, right? Look at the second integral here. We have r and 1 plus r cube here. So r divided by 1 plus r cube, okay? So when r goes to infinity here, the integrand here will tend to 0. So whatever value of theta we have here, the integrand here is going to be 0 in that limit, and limit r goes to infinity. So simply this integral will give me 0, right? So I can simply write down this integral next to that, e to the I theta star. Can simply take this out. So infinity to 0 dr over 1 plus r cube e to the I 3 theta star. Okay? So this is what I want to calculate. Okay? Let me erase this here. Okay. So when I look at that, okay, well, this integral looks like that, except this term here, e to the I 3 theta star. Okay, so now this is the time that we should determine what this theta star should be. Okay, so if this term was 1, okay, I would have dr over 1 plus r cube, and r here is also a real variable, okay, and these two integrals would be the same. Okay, so this is a good observation. So e to the I 2 pi is equal to 1, right? So then e to the I 3 theta star should be equal to 1. Okay, so 3 theta star should be equal to 2 pi. So theta star is equal to 2 pi over 3. So if I choose theta star as 2 pi over 3, which is equal to 120 degrees, right? So we will only include z1 here, so we are safe. And this integral will be similar to that. Okay? So let's insert the value of theta star here. So this becomes 1, and this becomes e to the I 2 pi over 3. Okay, very good. Well, look at the limits. It's kind of flipped, right? Otherwise they would be the same. So I simply multiply this with a minus sign. So this is minus So I change the limits here. Okay. So this is exactly the same integral here, right? So this is, if I call it I, this will be also I, right? Which is the integral I want to calculate. So the contour integral is simply equal to that. Okay, so if I call this as the contour integral, this is equal to that. Okay, very good. So now we are ready to work this out a little bit. So this will be I, can take I parentheses. So it's going to be 1 minus, so cosine 2 pi over 3, right? So we have cosine 2 pi over 3, and we have another minus sign here, minus I sine 2 pi over 3. Okay, so this is equal to I times 1 minus, so cosine 2 pi over 3, we are in the second quadrant. So the cosine is going to be negative, right? So cosine 120 is equal to, then plus, so it's going to be minus 1/2, right? Then we have minus I. Okay. So what is sine 2 pi over 3? So sine 120 degrees, right? So it's going to be positive square root 3 over 2. Okay, so this integral, I contour integral, should be equal to our goal integral times, so this becomes 3 minus I square root 3 over 2. So we already showed that the left hand side of the previous expression is equal to our goal integral times 3 minus I square root 3 over 2. Okay, so the next step is to calculate this residue of f of z. So f of z can be expressed as 1 over z minus z1, z minus z2 here, and z minus z3. Okay. Okay. This is going to be equal to, so we can use partial fraction decomposition, so a over z minus z1 plus b over z minus z2 plus c over z minus z3. Just a quick reminder, okay, the residue of f of z at z is equal to z1 is simply equal to limit when z goes to z1, z minus z1 times f of z, right? Okay, so if this is how we define it, by the way, as we see here, z1, z2, and z3 are all simple poles, okay? These are all simple poles. So when I use this definition here, so when I multiply this side with z minus z1, so this term is going to cancel. So these terms will have z minus z1 and z minus z1 here at the top. So since z1 and z2 and z3 are not the same, so z1 is not equal to z2, z1 is not equal to z3. Okay, when I take this limit here, z goes to z1, these two terms will just disappear. So what I will end up with is a. Okay, so then a is actually the residue of this function at z is equal to z1. So I need to find what a is. Okay, so how do we find a? So we close this term here. So wherever we see z, we are going to put z1. Okay, and this is how we will calculate a. So a is going to be equal to 1 over z1 minus z2 times z1 minus z3. Okay, so this is equal to 1 over, so z1 is equal to e to the I pi over 3 minus z2 is e to the I pi, which is equal to minus 1. So this just becomes plus 1. Good. Then we have e to the I pi over 3 minus e to the I 5 pi over 3. This is good. So if I look at z1 and z3, okay, so when I subtract these two complex numbers, they have the same real part, right? Oh, so the real parts are going to disappear, right? They cancel each other out. If I look at the imaginary parts, so this is going to be, so as you may see here, this is 1/2 here, and this is square root 3 over 2 I, and this will be here minus I square root 3 over 2. Okay, because cosine pi over 3 is 1/2, sine pi over 3 is equal to square root 3 over 2. Okay, so the real parts are going to cancel each other out. So this will have the imaginary part I square root 3 over 2 minus I square root 3 over 2. Okay, so then I will have two of those, right? So this here is simply equal to 2 times I square root 3 over 2. Okay, twice of this imaginary part. Okay, so these twos cancel each other out. Okay, so I have I square root 3 here. Okay, when I look at here, the real part of e to the I pi over 3 is 1/2. So 1/2 plus 1 gives me 3/2, right? Plus I, simply the imaginary part of this, because z2 does not have any imaginary part, I square root 3 over 2. Okay? So this is good. So I can simply continue here. So I can put 2 upstairs here. So there is a factor of 2 divided by, so I can multiply by I here. So this gives me a minus. I square is minus square root 3 times square root 3 is equal to 3. So minus 3. Then I will have plus I 3 square root 3. Okay, in the last board, we calculate the residue of f of z at z is equal to z1, and we get this relation from the residue theorem. So all we need to do is now to solve for I, which is our goal integral. Okay, and we see a lot of i's here. Hopefully they are going to disappear in the end, right? So the reason is we want to get a real answer here. Okay, so we will not see any i's in the end, hopefully. Okay, we will see that. So first of all, let's multiply everything with 2. Okay, so this becomes 4 here. This is good. So then the other step would be I'll take 1 square root of 3 out here. So this is square root of 3 minus I, which is equal to that. Okay, this is good. On the right hand side, what I want to do is I want to take this minus upstairs. Okay, get rid of this minus here. It's going to be minus here, and it's going to be minus here. Okay, and the next step is to multiply this with 3 plus I 3 square root of 3. Okay, so what do I have in the end is square root of 3I square root of 3 minus I is equal to, let's say, 8 pi I. Okay, we still have a minus sign here, so I'm just going to put it here. So minus 3 minus I 3 square root of 3 divided by, well, square of the first term, which is 9, minus square of the second term. It's going to be I square. 3 square is 9. This is just 3, so it's going to be 27. But I square is equal to negative 1, right? So minus minus becomes positive. So 27 plus 9 is equal to 36. Okay, this is 36. So at this point, I can divide by 4. This one 4. This gives me 2, and this is 9, right? This is good. So what else I can do? I can put this I inside here. So this becomes 3I. So I square. Here I times I becomes minus 1. So this is just plus, right? Plus. It's also good. So then I can take 1, 3 out, right? So this becomes 6 pi here, right? 6 pi. Okay. Very nice. Very good. So we have square root of 3 minus I, square root of 3 minus I. Very good. So simply cancel each other out. So I is nothing but 6 pi over 9 square root of 3. Okay? So we can further simplify that. So if you divide by 3 here, so this is 2 pi over 3 actually, and if you multiply with square root of 3, this will be 3 here, this will be square root of 3 here. So in the end, this is just 9. And this is our answer. Okay? So as you see, the result of this integral turned out to be a real number, as we expected. And magically, or nicely, all these imaginary parts disappeared. This is all for today. I hope you enjoyed it. See you next time. Bye.